Welcome, students. I'm your professor for today's explainer on the upward journey of building construction. Now, as a quick note for our post-production team, please make sure those English subtitles are hard-coded throughout this session so everyone can take great notes. All right, let's get right into it. You see, construction isn't just about stacking materials. It's literally an applied science, a highly careful sequence of engineered steps designed to ensure the spaces we live and work in remain standing for generations. Today's agenda covers 6 key areas. We'll start with Introduction to Structural Oversight, look at essential materials, move down to the foundation and plinth, explore masonry walls and openings, touch on material errors to avoid, and finish up with a summary and knowledge check.
All right, Part 1, Introduction to Structural Oversight.
Students, I really want you to consider the profound implications of our foundational objective, ensuring safety, serviceability, durability, and sustainability. Think about it for a second. A building is kind of like a massive, complex symphony. If even one section is out of tune, if safety or durability is compromised in any way, the entire performance just fails. And this is exactly where the discipline of construction planning and project management steps in to save the day.
In a recent chat I had with a veteran construction project manager, they hit the nail right on the head. Oversight is absolutely everything. They aren't just out there checking boxes on a clipboard. They are actively coordinating manpower, managing resources, and maintaining incredibly strict quality control standards to enforce structural stability. They made it super clear to me that preparing schedules and assessing risks is what actually prevents fatal delays and massive cost overruns. Without this tight management framework, even the most brilliant engineering plans would just evolve into total chaos.
Moving on to Part 2, Essential Materials, specifically bricks and cement.
So let's dive right into bricks, which are basically nature's ultimate building blocks. Molded from clay and fired in kilns at just unbelievably high temperatures, they give us the immense compressive strength we need to bear heavy structural weights, all while naturally resisting fire. Pretty amazing, right? But to lay them properly, masons rely on some very specific tools. You got the trowel to expertly spread the mortar, the plumb bob to make absolutely sure everything is perfectly vertical, and a spirit level to keep those courses perfectly horizontal.
But here's the thing, bricks can't do the job alone. They need a binder. And the chemical composition of cement is a lot like a highly precise baking recipe. The exact percentages of lime and silica completely dictate the ultimate durability of the wall. Lime is the absolute star of the show here, making up 60 to 67% of the mix, and it's directly responsible for the cement's overall strength. Silica steps in to boost that durability even further. And alumina? Well, even though it's only 3 to 8% of the mix, it acts as the crucial catalyst for quick setting.
Which brings us to Part 3, the foundation and plinth.
The step-by-step process of building a wall actually starts deep, deep underground. We have to establish rock-solid stability before we ever reach the visible floor level. I mean, we can't exactly just drop a building on the grass, right? Geotechnical engineers have to investigate the soil first. Only after that's done do we construct the actual foundation, build our way up to the plinth, and finally apply our moisture protection.
Think of the foundation like the root system of a giant tree. It absolutely must safely transfer immense structural loads down into the soil to prevent uneven settling and guarantee overall stability. If you're making a mental checklist for inspecting foundation stability, it goes like this. It must distribute weight so the pressure doesn't exceed what the soil can bear, it must prevent sliding, and it has to resist upward forces. Depending on the soil, we use shallow foundations, like isolated footings, for your standard homes. But we completely shift to deep foundations, like piles, when we're dealing with high-rise buildings on weaker ground.
Okay, moving upward, we hit the plinth. This acts as a sort of protective pedestal. It raises the building up and literally blocks rising moisture using what we call a damp-proof course, or DPC. The plinth is really your building's frontline defense against the ground itself. It elevates the living space above potential flood levels and keeps all that masonry wall above it nice, dry, and secure.
All right, on to Part 4, masonry walls and openings.
Here we get to see our complete vertical journey, rising seamlessly from the PCC bed and footing all the way straight up through the brick wall to the parapet. Notice that dividing line right at ground level? That's key. Everything below that line is the substructure, doing the heavy lifting of transferring loads to the earth. And everything above it? That's our superstructure, which actually encloses our space and gives us thermal insulation.
Now I want you to notice the really clear separation between the RCC lintel, which carries the wall's weight over the window, and the chaja, that small slab you see projecting outward. Think about it. When we punch a hole in our masonry wall for a window, the wall right above it suddenly loses its vertical support. The lintel bridges that gap perfectly, transferring the heavy load sideways to the adjacent solid walls. Meanwhile, the chaja is basically acting like a permanent umbrella to protect that opening from the rain.
Next up, Part 5, Material Errors to Avoid. So the absolutely crucial takeaway here is avoiding these incredibly common errors. Just like throwing way too much salt into a recipe ruins the whole dish, excess lime causes cement unsoundness, and excess alkalis cause something called efflorescence. Now, unsoundness means the cement will actually expand and crack after setting, which fatally compromises your entire masonry wall. And efflorescence? That leaves this powdery, salty residue that really degrades both the strength and the aesthetic of the structure. Stick to the chemical recipe, folks. It's totally non-negotiable.
Finally, Part 6, Summary and Knowledge Check.
Students, please make sure to grab this final reference for your notes. This is the absolute path of load transfer, from the roof slab all the way down to the soil. Gravity never takes a day off, right? The horizontal slabs you walk on transfer their weight to the horizontal beams. Then, the beams push that weight right into the vertical columns. The columns drive it straight down into the foundation, which finally spreads it safely out into the earth. It's a chain reaction. If any single link in this chain fails, the whole structure fails. To wrap things up, I'm going to leave you with a quick, short quiz to really test your understanding. Which precise chemical ingredient in our cement recipe forces it to set quickly? And what happens to the structure if we get that exact percentage wrong? Think back to our table earlier. Yep, the answer is alumina, which has to sit right between 3 and 8%. Now, what happens if a construction manager fails to enforce quality control and a bad batch of cement ends up compromising the foundation's load transfer? The consequences, guys, aren't just structural. They are massive matters of public safety. So as you review your notes tonight, ask yourself this. If the foundation of a building fails, was the true failure in the soil or was it in the oversight? Keep thinking on that. Class dismissed.